Коллеги, добрый день. Я думаю, можно начинать. Хочу поприветствовать вас на мероприятии лекции Янеза Законьшека, эксперта мирового уровня, постоянного члена комитета B5 СИГРЭ. И для приветственного слова вначале хотел бы предоставить заместителю министра энергетики Евгению Петровичу Гребчуку.
Дмитрий, спасибо. Слышно, видно меня?
Да.
Спасибо, уважаемые коллеги, дорогие друзья. В первую очередь, разрешите поприветствовать вас на этом мероприятии, на открытой лекции Янеза. Лекция проводится в рамках проекта нашего совместного Министерства энергетики Energy Talks и проекта молодежной секции РНК СИГРЭ «Открытые лекции». И тематика сегодня достаточно интересная, инновационная, и я думаю, что вот этот зарубежный опыт применению цифровых технологий в системах автоматизации, управления технологическими процессами электроэнергетики, он, естественно, будет полезен, и надеюсь, что тот опыт, с которым Янез поделится, он будет нами воспринят, и, конечно же, пища будет являться пищей для размышлений, для внедрения интеграции в наших энергосистемах. И новые технологии – это то, что диктует сейчас, по сути, новое время. Меняется технологическая парадигма, меняется технологический уклад, процессы внедрения активного цифровых технологий, интеллектуализация сетей, интеллектуализация энергетики – это то недалекое будущее, в котором мы уже живем. Поэтому, конечно же, сама лекция и тематика, она очень интересна, как я уже сказал, и полезна. Поэтому, наверное, всем желаю продуктивной работы, продуктивной лекции, и мы надеемся, что подобные лекции будут продолжены нами совместно с нашими партнерами. И все эти лекции приведут к большему пониманию и осознанию того, что творится в мире, и возможности внедрения и проекции этого всего, выбора лучших технологий, проекции их на российскую энергетику. В любом случае мы, как Министерство энергетики, всегда остаемся открытыми, остаемся готовыми к диалогу, и, надеюсь, этот диалог с помощью наших подобных проектов мы сможем выстроить. Еще раз спасибо всем участникам и желаю спасибо лектору, организаторам, и желаю всем участникам плодотворной работы.
Спасибо, Евгений Петрович. У нас сегодня планировалось, что с приветственным словом выступит еще ректор, но по уважительным причинам он не смог подключиться, но тем не менее прислал свое видеообращение. Сейчас, коллег, попрошу его подключить.
Здравствуйте, уважаемые друзья! Мы рады приветствовать вас в стенах Московского энергетического института на лекции очень известного специалиста Янеза Законьшека, которая посвящена вопросам цифровизации в области релейной защиты и автоматики. Сегодня все профессионалы находятся в таком серьезном поиске решений, связанных с цифровизацией, и данная лекция – один из путей решения данной проблемы. Я полагаю, что международный опыт использования процессов цифровизации, накопленных инноваций будет крайне полезный для той аудитории, которая сегодня будет присутствовать на лекции. Я всем желаю продуктивной работы и хорошего обмена мнений сегодня.
Предлагаю приступить к лекции. Янез, передаем вам слово. Спасибо, что смогли сегодня включиться.
Добрый день, уважаемые коллеги. Как первое, не знаю, вы меня слышите?
Да, я не слышно.
Слышите? Ну, как вторая, не знаю, как потом включить мой экран, как бы вам могу представить здесь. Так что можете... ага, есть уже мой экран. Видите?
Да, да.
О, отлично. Значит, я рад приветствовать вас на мою презентацию. И в течение многих лет я сотрудничаю с российскими специалистами, и у меня много друзей в России, видел тоже здесь некоторые, и мы с ними часто говорим по-русски. Но сегодня моя презентация будет на английском языке из-за большего объема специальной терминологии. Так вы все можете задавать свои вопросы как на английском, так и на русском языке. Но только несколько слов a few words about myself. So I got Master of Science degree in Power Engineering in 1977 in Ljubljana, Slovenia. After that, I was 15 years with Iskra company in Slovenia. That was completely different than it is today. And during this period, I had my first visits to Russia, where I discussed high-frequency power line carrier equipment. After that, I went to ABB Relays in Sweden for practically 15 years. And for 4 years, I was responsible for business and technology development in ABS Holdings in Russia. Since September 2009, I founded my own company, Relarte, and I'm director of this company, which is mostly consulting company here in Slovenia. And I am as well included in company NLAB in Russia, in Cheboksary, where I am working like a technical direction. And what I feel very important for my, let's say, all this life is professional life, that I was also all the time included in the international SIGRE organization. This way also a little bit in Russian National Committee of SIGRE Study Committee B5, which makes me really glad that people there accepting me as one of their common members. Just to a little bit, what shall I talk about? So I should talk about the transient, let's say, from older technologies to very modern ones. So I will start a little bit about relay history as most of it. And here I will also try to explain some expressions which we are talking today around the world. A few words about phasor measurement and wide area monitoring, protection, automation and control. A little bit about optical communications, because I believe that all this is very important, that we came today to this kind of digital systems, let's say, which are especially from protection, control and automation point of view very much based on IEC 61850 standard. And then I will show a little bit how we are going towards modern power systems. Maybe to say a few words about how do we really need this and why do we need this, and a couple words about smart grids and modern industry. Later on I can try to answer on your questions if there will be some of them. So if we go a little bit to development of protection, especially protection, but later on also automation and control, it in fact started already even before 1900 with electromechanical relays. So they mostly are doing amplitude comparison, which we say that they are analog relays. And a little bit after 1960, we came to static, solid states or electronic relays. Why did we call them during that period static relays? Because there was nothing inside which was moving, like in electromechanical relays. But they were generally operating from the very beginning as analog comparison relay. But later on, we came also somewhere around 70s, 68, 69, 70s, we came to so-called phase comparison, or what they called during that time digital relays. And I will try to show you a bit later on why they should be, or why they were called digital relays. After that, a little bit, already 1976, 78, we came into microprocessor-based relays. But at the very beginning, they were also analog relays. So they were not really what we are discussing today, how they are working with the algorithms and so on, and in digital form, as we say today. But later on, they came as microprocessor-based, also digital. And somewhere in 1980, as you can see, 3, 4, 5, they came numerical relays. So they were really calculating certain values, like impedance, or power, and so on. Here, it is also necessary to mention one very important moment when it comes to, let's say, computer or microprocessor-based relays. And that is already in 1969, Rockefeller, in fact, provided a very, very nice invention and description of how it should work fault protection with a digital computer. So you see, time when we are developing, let's say, relay protection, automation, to some practical use of everything can take very long time. Let's say even 69 to, let's say, 70, 80, 82. That means it's many, many long time before we really make something which is useful. So in this respect, I would like to show you how all this really worked. At the very beginning, even before electromechanical relays, they were using primary protection. So here you can see one very interesting picture how primary protection really worked in certain very old installations. But later on, it came really secondary, I would say, secondary protection, electromechanical. I put this picture here because it presents, I would say, something of the most beautiful. What I saw as electromechanical protection, this was line distance protection made by Braun-Boveri from Switzerland. And it was used for distance protection of very, very high voltage lines, let's say 400 kV, 500 kV, and so on, all around the world. Just for you to imagine how this was, it was approximately the height of this relay was over 1 meter. It was approximately 70 centimeters wide and deepness was around 35 centimeters. The weight of this relay was something around 50 kilograms. It was used all around the world and it's really something very nice. But, as I mentioned, later on they started with static relays. Here I will tell you about, not because I was working, I have been working in ABB and also with former ASEA, which was then together united with Braun-Boveri to ABB. But because during that period, this was absolutely the most let's say, producer of relay protection, which was had absolutely the highest technology. So it was also, let's say, here you can see a three-phase overcurrent protection, which appeared that time, and after that, this was also static protection. As I said before, static, that means electronic protection, which was one of the fastest on the world. I will show you later on how it really a little bit worked about that. Just to mention that, for example, this electromechanical protection relay, I have some experiences with it also when I was working in former 400 kV system in Yugoslavia. The shortest operating time of this relay was 8 milliseconds on 400 kV. After that, it came a little bit more developed static relay. That means with electronics and so on, but here inside the operation was digital. You will see later on how it really operated. And very similar, those two relays, the operating principle, let's say, were very, very practically the same, but this one here was already using microprocessor. But microprocessor here was used only for logic, to cope with logic and so on. And later on, we came to, let's say, a real microprocessor-based numerical distance relay. So just here, I would like to tell you only this. We are talking about microprocessor. And when they designed this relay, here it was called RELS 100, the capacity of microprocessor was not really big enough that it would perform all necessary functionality. So for making, let's say, to calculate impedance for phase-to-phase loops separately, for phase-to-earth loops separately, and for phase selection, they were using here 3 digital signal processors additional. So that was also very special approach, let's say, during that period. So just a little bit more, when we come to static relays, let's say, here is one busband protection, which was produced by ASEA in Sweden, introduced in 1970, with operating time between 5 to 10 milliseconds, and with minimum time to city saturation, which is maybe very important today, still 2 milliseconds. It means that if city saturated after 2 milliseconds, this protection operated always very, very reliable. And as it was so very fast, it is proven, there is reported a few times from all around the world that it has saved a human life. And it was used on all voltage levels, and we can say that it is proven that it was made more than 10,000 installations all over around the world. So it was really something very special. Then we come to ultra-high-speed line protection. It was also produced by ASEA in Sweden. Already in 1976, it was also a static protection. That means with electronics in these different modules. The total operating time of this protection was somewhere between, let's say, 2 to 4, 5 milliseconds. But here it was included also signal transmission from one end of the line to another end, which was using high-frequency carrier communication. And what is important, in order to get this very short tripping time or operating time, they were already during that period using static output. I can say relays, although they were not relays. They were transistors and electronic outputs. So this protection was used very much on lines which are going from northwest of United States and Canada down to California. And at the beginning, they were calling it traveling wave protection. But it was not really traveling wave protection because it was looking in changes, delta changes in voltages and currents for each phase separately on each line. And what is very interesting is that this principle, delta principle, has been very much used in China, or it is used also today. And they reported from Chinese companies in cigarette meeting, I think it was in Paris 2010, that 80% of operating time with this protection on power lines of very high voltage was under 8 milliseconds. Then we come to this RASFE relay, which was here you can see also static relay, but digital. Why digital? Because all the signals, current, voltage, how they were formed, everything this was changed into digital form. That means only 0 and 1. And then in the inside of the logic, it was decided whether fault or, for example, impedances inside of the protected zone or outside of the protected zone. So it means only digital form of signals was used here. What is important also is that it was called a full scheme distance protection. That means it has separate measuring elements for face-to-face and for face-to-earth faults. For each zone, separate measuring element, as well as it was using 6 independent phase selection elements, so that the phase selection was made, in fact, on other principle than only measurement of distance protection. It was also one of the first such relays in the world which was using quadrilateral characteristic for face-to-earth faults, and it was, of course, normal more characteristic used for face-to-face fault. The reason for this was that face-to-earth fault have to cover much higher fault resistance than, for example, face-to-face. And of course, also, as I mentioned before, distance protection numerical introduced in 1986. Also with different protection zones, separate phase selector, full scheme distance protection. There was power swing also, disturbance recorder with 1 millisecond resolution, and so on. Event recorder, even some fault locator was there. The communication schemes, permissive overreaching, underreaching, transfer trip, and so on. And it has 2 communication ports for monitoring and control. Already at that time, it has communication. So it was possible already in 1986 that, for example, protection engineer from office called this relay in substation over telephone link and got down, for example, disturbance records and so on. This was very first step towards such communication in the world. So we had here, it was possible to see that in fact the system has, we followed, let's say, like protection engineers and so on, all the time the needs and development of power system, as well as other supporting technologies. But here appears one question, but it was not sustainable. Why did I put this question here? With simply a reason, because whatever you talk today about power systems, about whatsoever in power systems, you hear people talking, oh, it should be sustainable, this is very important, and so on. But anyway, let us go a little bit on. So, because this is far away of being stopping development. So if we look into 1975, also from former ASEA, all protection devices and so on, everything for example, for one transmission line, very high voltage level, like 500 kV, was put into such relay panels. If we would look the same equipment with electromechanical relays, so this would be a wall approximately between 5 and 6 meters long or wide, however, as you take it. So this approach was already also one of the first steps towards integration of, let's say, I would say, secondary power systems. So here was everything what was necessary: distance protection, power swing, directional earthquake protection, AC and DC supervision circuits, stop protection, auxiliary relays, fault locator, and everything auto-reclosing for one circuit breaker, synchro check, and so on. Everything was in two such, we call them relay panels. And here, this was one thing which was also very important. Still, it was necessary to have very, very much of cabling inside of such substation, especially also because everything was general. I will show you later on some different approach, but generally everything, these all signals, everything was then transmitted towards the control house in substation over a huge amount of cables. We have here also control board, from which it was possible to operate the total substation, but it was also possible from control room in substation to maybe communicate to the control center somewhere, but that was either over telephone or carrier-aided high-frequency equipment. And I think that my little bit older colleagues, they know this even better than I do. But the life is going on, and of course they started with designing microprocessors somewhere around 71 or a little bit earlier before. And here I show you how really fast are increasing the capacity of microprocessor, for example, from Intel. And what was very important, and more or less it's still pretty close to this, Mr. Moore said that the capacity of processors, or let's say the number of transistors in microchips, will double every 2 years. So here you see, this scale here is not linear, it's logarithmic in a way. So here you can see how very fast everything is going on. And that was also one reason that, for example, already, as I mentioned before, first microprocessor-based relays were made already somewhere 86, 87, and so on. But then here was one, I would say, relay, but it was not anymore relay. We called him intelligent electronic device, IED, which took all this functionality into one such small block. Everything was inside. And also what is important, it was built in self-supervision. It was built in communication possibility, programmable logic, and so on. So when I mention self-supervision, here I would like to say that I see this approach as one kind of a first really serious step towards what we call maintenance on request today, because this was the possibility, or let's say one first step, really, as I said, to start discussing maintenance on request. They said, okay, if self-supervision says something doesn't work, that means we have to check the relay. Otherwise, maybe it's not necessary. Of course, it was not exactly like this, but it was close to this. And if you look today, what we have, today we have the possibility to be connected to all relays within the system, all IDs, and if something happens in the system, one fault, it is possible to, for example, download all disturbance recorder, not from this relay only, which should operate, but from all relays around. And on the basis of this, it is necessary also to determine whether they operated correctly or not, and make such a conclusion whether it's necessary to test them or not. And I know that in Russian, for example, in Russia, you have one such provider which can provide such systems, and I think that this is very, very positive. So what happened was that then we had these IEDs, and in generally, each IED has in input transformers and AD converter. Then it has binary inputs and outputs, like binary relays maybe, on different ways for different reasons. Each IED has got central processing units and communication part, I would say, and of course auxiliary power supply. There were generally possibilities to communicate between the units, for example, for certain protection or control reasons, and also to be connected in one system which was then connected to computer in substation, in maybe control room and so on, and maybe then also to remote control center according to different, I would say, how they were developing IEC standards. And what is important is I personally have such experiences, let's say, when we discuss this communication between certain units. You see, before interlockings in substations, they were designed by standard cables and so on, and it was many cabling, especially if these cables were going, let's say, to control room first and all. But it was possible then suddenly to make these interlocking signals and everything through such digital optical communication between different control IDs within the substation. This was one, for example, a possibility on how to do everything. Let's go now for another. So we were discussing now so far relays, relay protection, IDs, but I would mention here also one thing which is maybe today extremely important in power system protection. And so let us go back to Northeast blackout in United States in 2003. So during that period, it was more than 255 million people was without electricity between 2 hours and 2 days. Depends where they were during that period. This was one of the, let's say, if we forget what happened in Brazil 2 years before, I think that this is one of the biggest blackouts in the world which happened so far. And why I am talking about this? Because already in 1988, Aaron Putker and James Thorpe, they in fact designed phasor measuring units, PMUs. So, which were, of course, the Steinmetz was a theoretical, I would say, a person who theoretically defined so-called phasors and phasor measurements, but they really designed the physical equipment which was possible to measure these phasors, and at the same time, by using the global positioning system, GPS, they made possible to measure these phasors in a synchronized way. So out of that came the name of synchrophasors. So this is in one way very connected, because this invention was, let's say, much before, 5 years before this blackout, but the real use, practical use, studies of system stability and so on the basis of these PMUs was made only after this blackout in the United States. So I think I would not go very much into these details here. Just want to mention, because I know that this is in one way wide area. Let's say at the beginning it was only monitoring of these phasors and so on, so they were used mostly to study why something happened and so on. But today it is, as I mentioned here, that means it's protection, automation, and control of complete power systems, as you can see also here. The basic reasons for this, that we are using this today very, very much, are very interesting to look, and this is deregulated electricity market. I will have a little bit few words about this later on. Economy, economical reasons, pressure, it should be, everything should not cost very much. If you make some bad things in power system, then you have to pay this. And of course, communication technologies have improved tremendously during last few decades. So they really started on this way to use this, and I can say, because I know that this today in Russia you have huge number, I would say huge, but really big number of PMUs all around the country, and they have very special job to do, which is also one of the best important, is to be included in so-called, if I can say in Russia, because it's difficult to say in other ways, wide area protection and protihavarina automatica, because this has been developed in Russia, like even before, on old technologies, I would say on the top of the world when it comes to the quality and reliability of such systems. But as you can see here, wide area is not a system is a system protection, not equipment protection. So it protects the complete system. And it usually, as I said, is using communications all around. That means it needs also very good and fast communication. And it has minimum dependability requirements. That means if one wide area protection chain fails, it should anyway operate correct, and also it should have very, very high security. Otherwise, the costs are very high. Here is only one picture how to really do wide area, let's say, how to monitor, how to look everything. That means we are looking currents and voltages in maybe one substation with GPS, everything synchronized. We have special protocols. So we are transmitting voltage phasors, current phasors, frequency value, rate of change of frequency, and digital or binary signals if you want. And wide area monitoring system is giving just monitoring and supervision of data storage. It has interface to SCADA and so on, but control, wide area control system and protection system, they are operating over certain algorithms within the power system, and they go back, they send back feedback, protection and control reasons to the substation where they are used. The most important challenges, as you can see here on this picture, is to design, operate and maintain a very complex system. So, and usually this is very seldom called to really operate and act. But when it is called to act, it's extremely important that it does the job as necessary. And that is to save power systems from an uncontrolled blackout. I would say that this is one very important thing. So when we are looking at time scale, protection should operate very fast, even less than 10 milliseconds, and of course if it is something late, up to 1 second and so on. And SCADA system, practically not possible to work under 10 seconds, but even usually more, especially when people are included in. And wide area monitoring, protection and control, they are somewhere here between, so that they can work, let's say, from some maybe 50 or let's say 200 milliseconds and up to 100 seconds, dependent how the system is, what happens and how it operates. So if I again move to a little bit different, we have been now discussing very much important communication possibilities. So I already once showed this, this slide was made by my colleague Jorge Cardenas a few years ago. And here some people which were very, very important in development and studying of light are presented here. So one of them was Isaac Newton, Christian Huygens, and also Mikhail Lomonosov, which says between others that the light should be according to the wave theory. And of course, after that, Michael Faraday, which in 1845, you see how long time ago, he showed that the magnetism affects light in dielectric material. So why this is important? Because today, when we are talking about optical transformers, their operation is based exactly on what Faraday said. already so many years ago. And one more important thing is that somewhere after 1968, people started to look, our colleagues to look into the fiber attenuation. So you can see here that in Nippon, sheet glass made it in 68 decreased the attenuation from 1000 decibel in kilometer to 100. And in another 2 years, it came from 100 to 20 decibel per kilometer. And somewhere, let's say 1979 and 80, we came down to 0.15, let's say, decibel per kilometer, which is extremely success in this technology. So because practically we are today very, very close to technical minimum. So this was the reason which made possible communication also over optical fibers. So here I would just push back a little bit and go to protection, the relay protection again. And in 94, you can see pretty late, but it was designed line current differential protection, which was using direct optical fiber over digital communication. So that was also one extremely big move from previous pilot wire relays up to differential protection, which was based on optical fiber communication. And of course, we are talking about complete digital acquisition chain, but here I will talk only about optical current transformer. It was called Digital Optical Instrument Transformer and developed by ABB in 1985. What is interesting here is, I will put first this here, that it was used very much on series capacitors because it was necessary to have a current transformer up on series capacitors, very high voltage, so it was necessary to use some isolators, otherwise it would not be possible to use it. But what is important, although it is called optical current transformer, it was not optical. The measurement was done the same as in conventional transformers, magnetic transformers, so they were measured current, there was iron around with turns and so on, but electronics was done here inside of this transformer, let's call it this. So, and then optical fiber was connected to this electronic, and it is interesting that it was only one optical fiber. In input, signal was bringing also the power, operating power to all these electronics, which was sending out the optical signal, again values, of course, to electronic far away through, let's say, optical fiber. So that was something what was called digital optical instrument transformer. And the voltage was measured on the same way, only that for measurement of voltage they were using capacitor dividers in optical transformer, and of course then this was connected to voltage from secondary side, let's say from bottom side of capacitors. And today, as we said, we are using Faraday effect-based current transformers, which are looking into, let's say, phase difference between incoming and outgoing light, which is incoming into around current conductor, it comes back from the mirror, it goes back, and here we are doing oil processing and so on, which is called between other also low power instrument transformer or optical instrument transformer and so on. So this was one very important step also, and I can tell you that I was one of the member of a team which made in 1998 primary tests of such do-it transformer at Heles. This is system operator in Slovenia, and the results were simply, I would say, excellent. So then after that, this company decided that they will use these do-it transformers as for permanent installation on the 400 kV substation, but this in fact disappeared in one way because simply it was too fast. It was simply too fast, and there was no interest, let's say, to use these optical results and so on by other producers, and not even very much by ABB. So, but then we come to IEC 61850. So we have been discussing very, very much about communications, about digital, let's say, if we call them today, relays, electronic devices, and so on. So they were using many, many different protocols. And this was, in one way, very difficult for users because it was difficult to make one common system in substation. So it was necessary, in one way, to have vendors prepared to maybe make one common communication system, which would then make much easier development of substation automation devices and relay protection and so on. So an IEC project group, there was around 60 people, was established in 1995, and then they created a so-called IEC 61850 communication standard. So the main objectives of these standards were single protocol for complete substation, and of course then considering the modeling of different data and so on. But that was, first of all, at the beginning, substation protocol. Later on, it became power system communication protocol. So there was necessary to define basic services to transfer the data and mapping to different communication protocols. And there was necessary, or let's say the standard was in fact promote interoperability between systems from different vendors, and a common method or format for storing complete data. Let's say, of course, there was also testing and so on, which we can find a little bit maybe better in this picture. So everything was included here. Let's say system configuration was in one way defined. Structure for protection and control, how it should go. Especially communication between bay devices. Fault records were established still in COMTRADE format. Time synchronization for all of them. Ethernet standard was applied. So here I would just like to see, I showed you much older possibility to communicate via even optical fibers in substations before IEC 61850. But vendors were using other protocols. One reason why they didn't use Ethernet standard was because during that time let's say, so many years ago, Ethernet was extremely expensive communication. Today it is totally different, and so on. So what we have today is IEC 61850. It's a power system communication standard comprising 10 different, I would say, blocks with sub-blocks. As you can see, I believe many of you know now how this is going on. If you start reading all these materials and so on, it's a few thousands of pages. So it is a very, very complex, and I must say that it is still under development. I will show you later on why maybe this and what is still some challenges within this standard. And of course, what I would like to use in this opportunity, I suggest you look for a green book which SIGRE is going to publish about IEC 61850 standard. I hope it will be published towards the end of this year, or maybe very early beginning of next year. So here you will see a lot of how really to operate with this standard, what this standard show, how you should use it. I think that it will be presenting very much very positive results and also instructions on how to do your job in future. So if we are back today from that picture which I showed long time ago, first of all we have here on the top, we call it station link or station part of our 61850 standard. That means we are now communicating from different devices up on the top. Goose messaging, which was before used on certain, I would say, I made it here goose in such a way, so this goose messaging was moved also maybe up here, but then also here we made a process bus, as here was station bus, process bus, which is mostly today, I would say, still very much operating according to IEC 61850-9-2, which is in fact not standard. But then it was developed by UCA group just to get things more clear how to run everything this. But today we have IEC 61869-9 standard, which is discussing more also about how to transmit sampled values, which are coming today no more from, I would say, directly from transformers, magnetic transformers. You see here in these boxes there is no more analog input cards and so on, but they are coming from maybe standalone merging units which are located away from relay protection and connected maybe to conventional current and voltage transformers, or if you are looking into non-conventional instruments transformers, they go directly to merging unit, or they already have included this, and all these sampled values and signals are going then directly to certain parts of the substation and communication. So if we are going to use also maybe intelligent primary equipment, the system will be even more, let's say, different, because it will not be necessary even to have these direct communication cables, let's say maybe from protection to tripping, or from merging units, even they go sometimes to directly to circuit breakers and isolators and so on. So this is where we are maybe today, or we will be tomorrow. Maybe it is necessary to say here that this signals here, which are, let's say, used for station bus and so on. Such substations are today already many all around the world. But looking to substations with merging units and standalone merging units using sampled values and so on here, they are in fact not so many. It is still a lot of test installations all around the world, and it seems that it will take maybe even some more time before we will come to such design as it is presented here. It is one thing also here, which I have to say, maybe, okay, I can tell it here, that is a communication capacity. Everyone is talking, yeah, we have communication, it can communicate very good, but when we come to such really, I will say maybe kind of half digital substation or something like this, it's already sometimes an issue having enough of communication capabilities around here in maybe even station bus or especially also on process bus. Here I would like to mention just as example, as I learned, for example, some many years already ago now, one of the first such called digital substation in Moscow was made. I think it was called Ochakovo. And that substation needed to have more than 40,000 signals around in such buses because it's a very, very big substation. Now we come here maybe to process bus. If you have a big substation, let's say 20 or even more bays on some certain voltage level, even modern communication capabilities cannot manage such communication which is necessary, for example, for passband protection. So that is still a little bit of issue, but I will show you also maybe some other. Because, as I said, I would like to talk about challenges. And magnetic current transformers, I'm 100% sure, will remain in power system for many, many more years. There are very, very different reasons for this. One is price, one is their reliability, also to exchange them very, very fast. It has simply no economical reasons. So we will still need to live with them. And when we are discussing, for example, these merging units or standalone merging units, they will still get signals from such magnetic transformers. I have here a little bit, let's say, TPX and TPZ transformers, which has different time constant, secondary time constant. So TPX are transformers without air gap, that are having big air gap. And here you can see how they perform differently at big, maybe fault current with different time constant. So if you have, for example, two such different transformers, you can simply not use it for differential protection. But that is just one for information. The second one is how it looks like when these cities are saturated. And what is very interesting is that this is, I would say, something very normal today for such TPX types of transformers. And I heard many times, oh, before, many years ago, there was no city saturation and so on. But I don't believe that this is true, because if you were using, for example, electromechanical relays, then there was very big load, was inductive load of secondary windings of current transformers. So the current didn't fall like this down when the city saturated, but went something like this, and then it came down. So that was one of the very interesting things which we have to consider today. And what we have here is, for example, unsaturated secondary current from a non-remanent city type. So even if it is non-remanent city, it can go into saturation. But here it's unsaturated. So it shows, let's say, the difference, which I show also here. But here you see one saturated city saturation when on the secondary side of city is a very, very low resistance or impedance, very low. And that is the case, for example, which you will see in input transformers, maybe for merging units. So they can also go in saturation. And the guy who is developing a relay there, which is installed, for example, even few hundred meters away from here, and they get such signals from merging unit from sampled values, so they don't know this. So what will happen? Maybe again relay will operate for city saturation inside of the either relay or merging unit. So we have to consider everything this as a possibility which can happen also in the future. And I suggest you, if you want to have a little bit more of information, looking into a technical brochure 768 from Sigre. It was published in 2019, and there you can see much more about more details about this. But this is not issue only for magnetic conventional city type. If we look a little bit Rogowski coil, which is considered as low power or non-conventional instrument or current transformer, then it's necessary to consider also, which I would say not so many people know, that Rogowski coil signal really give you the IDT signal. So the change of current over time, this is what is really measured by Rogowski coil signal. And when we look into this, let's say we have primary current here. This is a black picture. Red one is what comes out from Rogowski coil, the IDT. Here we see the output when the current is interrupted, primary current interrupted to zero. Also, the IDT is going practically immediately to zero, very short time. But we have to integrate this current if we want to make, to use conventional, let's say, relay protection as we use it normally, so that it would be operating with this. Then the integrated current, when they interrupt primary current, the integrated current remains very high as a DC current for quite a long time. If nothing else, this can influence and initiate wrong operation of maybe breaker failure protection. So also these things should be considered when we are working with modern systems and digital substations and so on. Now we come to another one. We are coming to traveling wave protection. So I showed you before at the very beginning very fast protection, but it was not traveling wave protection before, although because at the beginning they call it even traveling wave. So you can see traveling wave is happening very early on when the fault appears in system and so on, and it is very short. So what is important, you can see one example of traveling wave here. It's only one at the beginning, which shows, let's say, time is moved from milliseconds to microseconds. So if we want really to detect a traveling wave as necessary to be sure that we will detect it and see it, then we need sampling rate of at least 100 megahertz or 10 megahertz is one, it's really great, but at least minimum 1 megahertz sampling rate. So compare this now to 100 kilohertz and so on, which we are now defining as much less also as a needed sample frequency for merging units and so on. So this means that we need to send 1 billion samples per second over process bus. And if we multiply this by 3 for 3-phase currents and maybe add some voltages, this is impossible to reach even with the most modern possible. So there are different ways maybe how to do this. They were discussing that they should maybe detect traveling wave in merging unit and send signal to the relay, but I don't like this approach because I don't think it is a good enough. Then we also have, let's say, of course, substations and so on. They are not only for high voltage network. We have to think also about generator protection. So if you go to generator reverse power protection, then angular accuracy of half degree or 1 degree is absolutely not enough. It should be better than 0.1 degree. Otherwise, it will this protection will operate in a wrong way. So this is also one thing which must be considered. Or, for example, which is also very typical for Russia, you have isolated or compensated systems, very much, even up to 110 kV, not only as distribution level, which is here, for example. So you can see that the primary fault current is extremely low in such cases. So, and not only this, but it is very, very low. It is also important that the angular accuracy for this very low current, fault current, must be very good. Otherwise, you will again get wrong operation of earth fault protection in isolated or compensated systems. And in this technical brochure, which I mentioned before, you will also see that we suggest that always the producer of merging units and also those which are producing non-conventional instrument transformers should provide their body diagram for frequencies, let's say, practically from 0 Hertz up to, let's say, at least 5-6 kilohertz, if not even more. Because only on this way, those which are producing, let's say, protection now, or measuring elements and so on, they will be able to do also correct functionality of their own equipment. Again, you can go into this technical brochure for see all this. So here I have made one picture which maybe some people will not like it. You can see here the picture of protection ID, let's say conventional, how it is designed. Everything is here. We have analog, or maybe, let's say, if we go for conventional cities in VCs, we have conventional input transformers, analog filters, A to D converters. Then we have digital signal processing, maybe logic and communication. It goes to station bus and so on, and binary outputs which are going to circuit breaker. in modern design, which we are talking about, we have one part of this is here, emerging unit. Yeah? And also input transformers, whatever they are, analog filters, AD converters, and digital signal adjustments. Sorry, to come to IC sampled values. They go then to process bus over Ethernet switch. After that, they go from here, they go into so-called protection ID, which is making logic and communication. Of course, here should be also calculate and digital signal processing. Yeah. So they do have some possibilities for binary input, binary outputs, but generally everything should go to station bus also, information. And from this digital signal processing, logic and communication, then it should go back to IEC 61850, like a goose message, and from here over the switches, again, like a goose message to, I would say, binary input-output merging unit or part of merging unit. So if you look into required communication time and process times here in between, we can come when its maximum times are reached up to practically 6 to 7 milliseconds time delay in this fault clearing time. So this is one. So we are having, for example, today modern traveling wave protection. The fault is detected, let's say, as traveling wave itself in, let's say, 200 microseconds, maybe then some communication links and so on, but we come to max some 3-4 milliseconds if communication is good, and we can operate in such time. But if we add everything this here, we come to, let's say, even more, 10 or 15 milliseconds. Why should we do this? I would also like to mention here, we are discussing very much HVDC systems. And in HVDC systems, not lines, but total systems, networks, then we have to have operating time down to, together with braking and so on, down to less than 1 millisecond. How will we reach this? I don't know. So these are challenges which are still coming. So if we go back here, that means we were discussing before very conventional design when these merging units are located close to primary equipment. Protection equipment is located maybe in control house or control room and so on. So now I would like to show you one picture which is also coming from, let's say, Slovenia. But such substations were designed in 1975-76. Already in that time, those engineers who were working on this, they said, why should we use so very much of cables? Cables are extremely expensive. So why should we not put relays, all control equipment for one bay, for a certain bay, inside of one small house close to a bay, which is very close to current transformers, very close to voltage transformers, just a few meters away, maybe 20, 30 meters away from circuit breakers. And they said we will save, first of all, very much of money, and as a second, the design will be also much better. It is so here is one approach, for example, all, as I said, all protection, control, and all such equipment, generally in such one house, is going for 2 bays, because the house is installed between maybe 2 different bays of the same level. And if you look today, that means we could maybe discuss still the possibility to have such relay in the same way as it was before, so that it will provide very good communication, a very fast operating time. It can be located in such house. It will go to station bus over 61850, and it can send out also, for example, sampled values or some other digital boost signals over to external process bus. And if you look at this picture, then we can look into, let's say, busbar protection. They called it distributed busbar protection, although this is under question if it is correct expression. But that was when the relays were used like this, and they were sending digital signals, for example, sampled values to the central unit for busbar protection, and then it has operated back into here. And at the same time, they were able to use here also another protection as backup protection in such systems. So what is going on today? You can see one design which all such equipment, which I showed today before in houses, it is located in such containers with air conditioning, and also the same equipment as before, it is used in containers. This is today quite pretty modern design in many high voltage substations. So we have reliable protection systems. We can have very fast operating time, especially if we would make also static electronic outputs. We have less hardware, shorter commissioning time, because everything this can be factory acceptance tested in factory. So you don't need to spend weeks or even months in substation, making station testing and so on. Everything this can be done even before. And also, you don't need to have, for example, as we discussed, for merging units, which would be just installed independently near to circuit breakers or transformers, cities and VTs. Then the temperature range should go, in fact, from -60 up to +70 or even 80 degrees of Celsius. So how will these merging units operate under such condition, and how long will be a lifetime of such merging units? That's a very big question. So we came here again into this substation. And I think that it's maybe really necessary to consider all such challenges also in the future. It is not that I would be against such modern design, such modern approach, but it is necessary to consider everything this very seriously. It's necessary to think about what we are doing. And as I said before, with all these intelligent devices and so on, we come into practically very low number of elements in form IDs. So why should not we maybe put all of these processors and so on into maybe one box, and put this station bus also in this box? And this way we are coming into special digital protection, control and automation solutions, which is called a central station. But anyway, we are increasing the reliability of these substations, decreasing wiring. We have much less engineering today. And we can process a station-wide station available information. We can even provide new functionality. So having everything this, we are going to much better functionality, and what we are calling today digital power systems. So why do we really need all this? That's again maybe one question. You see, I made this slide quite some time ago from 2008 about CO2 all around the world. And this carbon dioxide is really, it seems, getting very difficult for all our society. So if we look through the history, I will go through this very fast. This guy, few hundred years ago, did nothing bad. In 1900, maybe 20, even such factory was okay, acceptable. But you look these two pictures here. These are pictures on the carless day. So the day when no one should really use cars, and one picture is from Tokyo, another one is from Moscow. So this is what we are discussing with CO2. And then we are discussing to go to non-conventional, I would say, power sources, to wind power, to optical photovoltaics maybe, and so on, and solar power. So in 2009, there was suggested the Certec Eumena project in Europe, which would, as you can see here, connect practically all Central Europe here and Northern Africa, here this part, Turkey, and so on. What is interesting is that they suggested to use over Sahara this concentrating solar power, not photovoltaic. And of course, near the sea, everywhere, wind power, and so on. And all these should be connected with most probably very much of all these lines here should be high voltage DC lines. So this was one suggestion which practically is today totally dead. The reasons for this, I think it has no meaning to discuss why everything is fall down, but maybe it's better to look into this. So again, we have SIGRE technical brochure. It is 775. It was issued also in 2019, which is discussing transmission corridors all around the world as a network of the future. So we are looking into such networks, or they are, let's say, at least discussed between different parts of the world. You have Africa, Europe here, North America, South America, and so on. Here is also one connection, which was discussed here over Russia, down, and then from Russia to the United States. When you look this, I must say that not many people know that the border from Russia to United States is only a couple of kilometers. But anyway, so that means from Russia down to China, to Chinese system, maybe here over from Kazakhstan and so on, again over up to, and all these countries in Europe and so on. So this will be also DC system in the future. It's a question when it will happen, but most probably it will. So, but when we go again towards the wind energy, I want to discuss this. You see, maybe you know this picture. It is Don Quixote, which is fighting with windmills. And today, what we have today, it looks fantastic, really beautiful. But when you come into such area, then you ask yourself, how does it really look like? How it will work, everything all around the system. What is important here is that, first of all, when we are looking for very much of this, we will decrease power system inertia. And that is also one very big question also for wide area protection, for everything, how this will everything work. And of course, everything we have here, we have inverters, we have HVDC to AC inverters and so on. So I will not read this here. I can only tell you that with these inverters, when it comes to faults in maybe in AC systems, or even worse if it comes to faults in DC systems, it's a really big problem for the total system, and especially for controllers. These controllers of such inverters, electronic converters, they are making a lot of, I will say, problems to the operation of total systems. And now I must say that one way of doing things is that you think about what is going to happen when you will build up such a big system. So it is a Russian system. I think that you all know this picture from St. Petersburg, but I use this all around the world if I want to show how it is necessary to think about how your future system will look like, to develop such your future system, because only if you think, if we look a little bit, not many people know this, but if we look HVDC systems, in former Soviet Union, it was in fact a pioneer of such systems with one HVDC link, I think very close to Moscow. I forgot how it was named, I'm sorry. And the other one, which is also, people practically don't know about this, but in former Soviet Union, it was established or installed one 1150 kV system line, which was over 2,000 kilometers long, from down from Kazakhstan out to north towards Siberia and so on. And it was installed, in fact, practically 25 years before 1,000 kV system or lines were installed, AC lines were installed in China. So this is something tremendous. And it is necessary to remember everything this when we are going to do something new. And of course, today we are discussing testing different systems over, let's say, 61850, how they will work. We are discussing, as I mentioned, protection, automation, control, wide area protection, and so on. We are discussing smart grids and smart cities inside, and we are discussing multi-modular converters and so on, which absolutely will be used everywhere. So without really good test equipment, I made this picture not because I'm included in NLab Russia, but because more and more Russian companies and universities, also different other organizations are using this to really look and test and look what will happen in different parts of power systems, in protection, on smart grid and distribution and so on. So this is why I wanted to say. So when we come to smart grid, I'm slowly coming towards the end. I hope I'm not too long. I put here, according to IEC conceptual framework, you can always find these connections, this picture, how it is modern smart grid structured for today. And you can see that here are many, many players which are included in everything. If you go on site and look for this, then you will see that for every one of such players inside of modern smart grid, there is also one more such a very big picture with very more of other players which are included here in the system. I will not go to this. It is just that smart grid is today totally different than it was many, many years ago, the power grid. Then we go to Paris 2018, there was a keynote presentation. They were saying that we are now in the fourth stage, I would say, of industrial. This is fourth industrial revolution today. We have very much of data. We have cloud computing. Important, I haven't even mentioned, is cyber security, also for power systems, different integration, and so on, and simulation, and so on. So this is where we are living today, and what everything influence also the power system and energy inside of the, let's say, energy industry. You can see here different points, again, like cyber security, new service modeling. They are saying infrastructure is aging, and but we have reduced resiliency, they say, and so on. So I don't want to discuss this. I just want to show you what do we have here now, because we have so many players. And suddenly we are discussing the relation between dependability, security, and economy. So everyone out of these players wants, of course, to make also some money. So we do have really big issues in this respect, and we have to think about it. So who is responsible for what? When we have so many people, of course. If they don't find the good reason, then we have really big problems. And we come into such issues, let's say, even today. That's why I decided to show you what happened in continental Europe, synchronous area, in 8th of January this year. So in this substation here, which is called Ernestino in Croatia, one circuit breaker simply opened, and in the very first or a few of initial reports, it was saying, sorry, overcurrent protection operated over the bus coupler circuit breaker. It interrupted everything this, and then it started. New line has also go out of operation. Very much happened here also in Romania. Distance protection operated and so on, but they managed in this western part of Europe because they very fast disconnected one very big user. It was disconnected, I think, 600 megawatts of use and so on. So kind of they managed to keep this system. But as reaction on this, even Turkey reacted here. So what was here a problem? Oh, again, the relay protection, which is always the first one who is responsible for everything what happened. But this was not, let's say, a very simple overcurrent protection which would operate for certain fault. This was overload protection, which prevented overloading, which went from this southeast part of Europe towards southwest part of Europe again. So we have interim report, and but final report I was not able to find it. Only 2 months after this event, the ENSO-E and the Acer group, Acer organization, they decided that they will make again total investigation together on the basis of some very complex documents which defined how it is necessary to work after certain such events. But let's leave us this one now. Here we go to February 10 to 20, what caused very huge decrease of electric power in Texas in United States. Again, if you look what everything happened, how many people, how they were freezing, they couldn't get any heating, they were sleeping in cars, and there was no more petrol in the car, so they were again freezing and so on. So the final conclusion which you can take is power companies have absolutely not been prepared for such operating conditions. So when you have, if you go to internet, you try to see a little bit of pictures. I think that it was really cold, yes, but to make everything like this, it's really very bad. And here you can see how it was with the consumption of natural gas, coal was weighting down, nuclear went down, because it was simply not possible to send this energy to consumers. And one more thing, because it is energy market operating, so that some users, which usually paid $50 per month for electricity, they had to pay even $1,500. They got a bill for this. And what not many people really know, this is Texas. This is, in fact, south, I would say, east of United States. But at the same time, there was such kind of blackout also in Oregon, which is northwest of United States, and more than 200,000 households remain without electricity also there for quite some time. And what I was really shocked, I decided to put this picture here to you. Just a few days ago, I in fact learned that they have today very big troubles in South Africa because they don't have enough of resources to produce the electric energy which is consumed by users in South Africa. So dependent on weather conditions and other conditions, they have two possibilities. They have reductions 2 hours a day, once 2 hours a day for each of households, for each one, or if the conditions are very difficult, 2 times 2 hours a day, they simply stay without electricity. So it's very interesting because I remember when I was very small kid, some 6-7 years old, we had also this in old Yugoslavia because there was not enough of production, but later on they made really good systems. So now here in Slovenia we have absolutely no such troubles. So this is, I hope I was not too long. That was too much. I don't know if you are satisfied with my presentation or not, but this is what we have in the moment. Thank you very much for your patience.
Янис, спасибо большое вам. Несмотря на то, что, да, действительно, лекция получилась немножко длиннее, чем мы планировали, но она была настолько интересная, что, я думаю, что никто и не заметил этого времени. Вот. А сейчас, действительно, если у кого-то есть вопросы, коллеги, воспользуйтесь, пожалуйста, службой Webex. Там есть кнопка «Поднять руку». Собственно, мы тогда включим вам микрофон, чтобы вы могли свой вопрос.
Меня слышно?
Yes, I hear.
Okay. Good afternoon, Yanis. My name is Aidar, and I would like to thank you say thank you for your such an interesting lecture. It was really useful to know some history about relays, about relay protection, and the future maybe, and the future of the modern grid. So my question is about digital substation. As you said, with developing such system, the load increasing on the process bus and sometimes on substation bus because of a lot of measurements from merging units.
Yes.
But can we decrease this load on the process bus on the network by using synchrophaser, like in PNU? Will it somehow mitigate this much load on the network, or it will cause a lot of problem for us? What do you think?
You see, if you go to synchrophaser,
yes,
synchrophaser gives you the amplitude and phase angle of a certain let's say current or voltage. But when you come to real protection needs sampled values to operate very, very fast. So, and also as I presented on my picture before, these values are not used for this protection, which should operate very fast. Because, as I said, you see, modern systems, even the inertia of systems is going down. So what we discussed before, that let's say protection needs to operate in 25 to 30 milliseconds in order to go to let's say circuit breaker, and circuit breaker will open and it will be total fault time in system will be 100 milliseconds. That is absolutely, it's getting, we are coming to the system where the system will not manage this so very fast operation anymore. It will need to operate even faster. So, and in that case, these sampled, these synchrophasers cannot provide such a very fast information to algorithms of protection to really operate like this. This is a point. Maybe, I agree with you, it's necessary to look. Maybe it is possible to go with kind of synchrophasers. So I can give you one example now. I was discussing, or I mentioned the one of the first current differential line protection, yeah, which was using optical fibers for installation. At the very beginning, this protection was in fact, if I would say like this, using current synchrophasers, because it was sending, I think, now I don't know anymore exactly, but it was sending value of current, that means RMS value, and it was sending phase angle. So that was at the beginning. But today, all these protections are sending over optical fibers, in fact, sampled values, because they provide this way much faster operation of protection. So I think that it is necessary to look into such possibilities to see what would be possible to use and what would not be possible to use.
Okay, thank you. I see.
You're welcome. Thank you. Yes, some more? I don't hear anymore. Sorry.
Another one.
Okay.
Hello, Yanis. Are you hearing me good?
Yes, I hear you.
Firstly, I want to say thank you for the lecture, because it was very interesting information for me. My name is Kirill, and I'm a student of Electric Power Engineering Institute. Now I'm on the second course, but soon I'll be writing my diploma work on one of the topics, relay protection and automation. So, may you give me advice, please, what in your opinion the most prevalent topics for this nowadays?
So that you would make your work on this, maybe?
Yes, baccalaureate work.
Yeah, okay. Baccalaureate, that means you are after 3 years of study, is it correct?
4 years, yeah.
4 years. Okay, 3-4 years. Okay. That means, you know, I have problems with this because when I was studying, we had practically 4.5 years to study and then half year for diploma. That was totally different than it is now. Well, there are still some possibilities, in fact, to look into some maybe a little bit advanced algorithms for certain protections. You see, as I mentioned at the very beginning, distance protection. I said there were separate measuring elements for face-to-face, separate measuring elements for face-to-earth, and separate elements for face selection. So to really say which face is faulty. So that was, and that elements operated in a completely, I would say not completely, but they were using different information that those elements which were using for zone impedance measurement. If you go today, most of relays, distance relays, they are still using starting elements. And starting elements, no one asked why they were used. Starting elements were used in electromechanical relays because otherwise it would be necessary to have even more iron and copper wires and everything inside of these boxes. So it would be good to look if there is some other much better possibilities to determine which phase is faulty. Because to determine faulty phase, only phase, not distance to fault, because this is, but a faulty phase is important only really to make correct single pole tripping and auto reclosing on high voltage lines. And there is even more. Today it will be necessary to go also for face-to-face faults, because I don't know if you have seen, but in Germany, for example, they are discussing that even for face-to-face faults, they would open only one phase. One of two faulty phases and open and then close them again. So it would be kind of single phase operation on two-phase fault. After that, there is also one interesting thing which has been known, especially in Japan, and also I think they are using it now in China, is on double circuit parallel operating lines. They are having, I forgot how to call it, they have a special tripping and auto reclosing when as long as they can keep, let's say, out of 6 conductors on such line, they can keep 2 healthy phases. That means maybe even one phase on one circuit and another phase on another circuit, they are still making auto reclosing and single pole, or they call it multi-pole, yes, multi-pole tripping and auto reclosing. So this is what maybe for future you should also discuss and look in. But there is one another thing which I believe is maybe even more important, what is now, at least what I can see what's going on in Russia. So in Russia, as far as I know, please if I'm wrong, tell me, very much is, let's say, everything is looking towards the north of Russia. How it will be up on the north, producing gas on the north, let's say, oil to get it out So many people will need to live up on the north. There will be, I think, that there will be some kind of very important microgrids with different resources which will produce this electric energy. So for these microgrids to provide reliable protection, it will be very, very demanding job. And maybe this could be something what could be interesting for you also. That means protection, maybe even control and automation, because you cannot split this anymore today, I think, of microgrids which will be developed up far away on the north of Russia. It could be even much more. It could be much more, but I think that these are maybe some really important things.
Thank you, Yanis.
Okay, thank you.
You are welcome.
Anybody else? I think it's all.
Okay.
Thank you very much, Yanis.
Thank you very much to all of you.
Soon we will meet in a different place, maybe in Paris, maybe in Moscow, I don't know.
You know, honestly speaking, I am missing very much Moscow, honestly speaking. To go there, to see again these very beautiful metro stations and so on. And you see, I have put this here picture. As you can see, it's still on my screen. It's Cheboksary, which I also like very much. The protection city of Russia. And I would like to thank you very much. Большое спасибо за внимание. You can see this my beautiful lake, and you are always welcome to meet me also here in Slovenia. Thank you very much.
See you.
See you. Thank you. Thank you. I got some messages. Thank you very much, guys. I'm really glad. Thank you. Goodbye.